Thank you, Tom. So, yes, it's actually 8 years and 4 days since I've been here, and I've enjoyed almost all of them. So first, a little bit about me. Spectroscopy is what I love. It lets you do so many things. It lets you look at atoms, it lets you look at molecules, and what grabbed my attention is that you can look at stars. You can tell how hot they are, you can tell how fast they're moving. And that's really important. So what I spent a lot of my early professional life doing was looking for planets. And it's fantastic coming back now to LASP, where Kepler is run where you actually can see this. I was told in my PhD oral examination that I really shouldn't waste my time doing this sort of thing because it would never be possible. But there's further to go. We now know there's planets. Is there life on those planets? I think that is a really big question, and spectroscopy can answer that. You can look at the atmosphere of these planets and try and detect signs of life. So that's not what I do anymore, but I think that's the next step in this thing. So as Tom mentioned, I've played this game an awful lot. One of the fun things and difficult things about being an instrument scientist is you normally get called in when something doesn't work. And the moment you fix it, they say thank you very much, and you go and look for the next job. So I started out in Europe, England, then I moved to Holland, Spain, Germany, Denmark, France. Had a quick trip down to South Africa to deploy an instrument actually for trying to find planets. Moved over to Tucson, USC, and now 20-something years later, I'm in Boulder, and I really love it here. So the red spots are where I've sort of had jobs, and the blue spots are where I do stuff. So it's a quite nice smattering over the map. And then spectroscopy, you look at light, and as my career has progressed, you can see I'm gradually moving down to these short wavelengths, and guess once we get to gammas, I'm going to have to retire. So this little bit here is the visible. We work here at LASP mostly in this EUV, and we're moving down into the XUV and soft X-ray range. And this is really exciting. And one of the exciting things is that it's very difficult to do it. So resolution is a measure of how accurately you can measure these wavelengths. So these things out in the optical, you can just measure it fantastically well. Eve, which is this red line here, going from late 2008 when we first had the instrument on. So if we've got a resolution of, a few thousand, the X-ray and other stuff, there just aren't enough photons to measure this. And what's worse, it's difficult to measure them accurately. So that's a challenge. I put this up here just because I always seem to build these cylindrical instruments. This could be a rocket payload. If you look at the rocket payload outside, this looks just like it. This is my first, or actually the second version of a planetary search spectrometer. This is actually a fantastic instrument. In 1984, we could measure the radial velocity of a star, so that's how fast it's coming towards you, going away from you, to within 10 meters per second. A couple of years later, on a much bigger telescope, we're doing sub-meter per second measurements on stars. So this is the other way of finding planets. Kepler looks for planets by looking at the star, and if a planet goes in front of it, the light curve drops, so it's photometry. This is actually looking at the star coming towards you a bit, because the gravity of the planet is pulling the star towards you, and then as the planet moves away, the star moves away a little bit as well. There's also another way of looking at spectrum. I've done quite a lot of work in Belgium, because they built some solar instruments as well, and if you stack Belgium chocolate up just right, you can make it look like a solar spectrum. So, as Tom said, I'm what's called an instrument scientist. So how I see this job is that I am the interface between the science community here and the engineering community here. And it means you need to know a little bit about an awful lot of things, but I'm not really a specialist in anything. It suits me fine. I define what the measurement that new instruments should make. I need to understand how that instrument is calibrated and what the uncertainties of the instrument are. And also sort of what modes that instrument has to operate in that we can make those measurements. Sort of, you don't just let an instrument stare at the sun, for instance. You have to have various calibration modes to see what your detector's doing, what your filters are doing. So part of my job is sort of defining what those modes should be. As I say, this is absolutely perfect for me. I love this. Similarities between science and engineering. Number one, I look at the LASP people here. It is the most creative bunch of people I have ever met. It is fantastic. We try to find elegant solutions to the problems. We design and build, test these instruments. We try to understand what's worked well in the past and what hasn't worked well, and how applicable that is to what we're building now. It's sort of, you can't just say that didn't work, because you have to understand why it didn't work. Because it may be the perfect solution for what you're doing now. So it's a large problem space. And I think finally sort of the one word which drives everything. I read Zen and the Art of Motorcycle Maintenance in college, and quality doesn't necessarily mean sort of the best possible, most expensive everything. It means as a whole we build stuff which is quality. Now of course there are differences as well. So an engineer will come and ask me, well, what are your requirements, Andrew? I say, just do the best you can. Well, you know, better's the enemy of good enough. Do it better then. I'll write better requirements in that case. I hate that phrase. I also hate failure is not an option. Failure has to be an option. If you don't fail doing something, you will never, ever learn. So I think one of my little political rant, one of NASA's problems is they are so scared of failing because it costs so much money to do this, that sort of you don't make the sort of progress you need to be making. Failure has to be an option, and I think that's one of the really exciting things about things like CubeSats and rocket instruments, because they're fairly cheap, and you can try these new things before you go and sort of spend $1 billion, and you just definitely don't want that to fail, but you have to be able to do new stuff. And as I say, sort of, there is an art to this, and creativity is that. So what do I actually do? I try to make better instruments. And I try to do this by understanding what's going on with the instruments we have. So I calibrate instruments so I actually know what they're measuring. Degradation is something, once you start, especially in the extreme ultraviolet, the photons are so energy that the photons have so much energy that they start degrading anything they touch. So not only may you not know what you're measuring, it may be getting worse as well. And quite a lot of this, sort of certainly in the soft X-ray region, we just don't make the measurements. And that leaves the models totally unconstrained and lets the modelers be happy. So I think one of the things I understood while putting this talk together, my goal in life is to make modelers unhappy. That's, I sort of have known this in the background for a long time, but I think this is a big thing. So one of the ways I do this is that I look at the data from different instruments. And in my case, sort of all these instruments are looking at the sun. They're all looking from just about the same place in the orbit most of the time, so they're looking at the same sun, and they give different answers. And not only do they give different answers to what their quoted uncertainties are. And this has been just driving me for probably the last 10 or 15 years, is to understand why this is the case. And why I want to do this, sort of, I want to learn about the instruments, why is this happening? We want to provide better data products for the community, sort of. this is sort of really nice, but sort of it's really important to the space weather people. They really want to know what the EUV and X-ray fluxes are. So there's a whole community based off this, and we want to be able to do better in the future. So back in 2006, this was actually the first graph I could find, and there were only 2 instruments measuring in basically the helium-2. It's a helium ionization line at about 30.4 nanometers. And on SOHO, there's this instrument called the Solar EUV Monitor, SEM. It launched in 1996, and it was the only instrument measuring this. Then in 2002, Time-C launched, and it had another instrument measuring that, and so we could compare the data. And it wasn't bad, actually. This is after more than 2 years of work to get it this good, but this isn't bad. Now we can do this, though. We have lots of instruments. So starting way back here, SOHO, Time-C, then Lyra came on board, then, well, sorry, the GOES EUVS came on board, and Lyra came on board, and Eve came on board, and we now have all of this data. And one of the nice things about this particular data set and this solar cycle is that round about here in 2007, we had a set of solar rotations where really one active region was coming and going and coming and going. And this can tell you an awful lot about what the different instruments are measuring.
What was coming and going?
There was so the sun's rotating, and you have an active region, which is sort of just a little, in the UUV, it's a bright region, and it comes and it rotates around the disk and it goes around the back and it gives you this beautiful little oscillation. So the first thing, which I'm quite proud of, this sort of, all these curves are now within about 10% of each other, and there is no massaging there. All I do is I take what the instrument bandpass is, and I plot their data, divide by the bandpass, and you know, it's not a factor of 2 off, which it was 10 years ago. So what this tells us is, it tells us something about the plasma emitting this radiation on the sun. If you have what's called an optically thick plasma, which is actually typical of this helium emission, the photons come out, but if they see more of this helium plasma, it will absorb it. And so when you see stuff at the limb, it's really just this little box of plasma here is making the light. Whereas if you have a thin plasma, the light emitted by the gas behind the absorbing thing will just go straight through it. So you see a characteristic sort of a bump at the edge because there's more, you're looking at more of the light. And so this is an image from AIA on a fairly quiet, very quiet solar day. And you can see in helium the image is fairly flat, whereas in this optically thin ion line, you can see there's a bright ring around the edge of it. And so this really lets us examine what the instruments are doing which are measuring this. So what I've done is I've gone and looked at one of those cycles, and on Eve we can measure just that helium line, and you see as the active region rotates, so this is, I should say, this is time down here, and you're watching an active region come onto the disk, rotate around it, and come off. And you can see it comes on, it peaks about in the middle, and it goes off again. Now what we see in the SEM instrument is that it peaks earlier, it has a little dip in the middle, and then it goes back down. Now unfortunately this isn't a typical example in the, almost 20 years of SOHO. I've only found 4 or 5 examples which are this clear. But it does show that the SEM has sensitivity to optically thin emission lines, which are typically sort of at 17 nanometers, and this is meant to be measuring at 304 nanometers. And so we knew this, and we could not explain it. But what drove this is that we wanted to make, SOHO is getting very old now. Money for funding it is running out, and it's making this measurement which the space weather community rely on. So we really need to understand what was going on so that we could make what's called a proxy. We could make a model of the instrument using other data so that once SOHO goes away, and specifically SEM goes away, this data set isn't gone for good. So we looked really carefully at the instrument and found out there's actually a way for light to bounce off one of the side walls into the detector. And when you measure the instrument response very carefully, you find this peak at 17 nanometers, and then this 304 peak, which is what it's meant to be measuring, and then this little long peak. So I can now use an instrument on SDO Eve called ESP, which has bands at 17, 25, and 304, to make a proxy measurement. So I can make a measurement which is almost as good as the SEM measurement. And this is now being used routinely by the space weather people. So as I say, this S10 index from SEM was designed to measure the helium-2. It actually turns out that including this other emission from the coronal lines does a better job of driving models of the Earth's atmosphere. It represents what the sun is doing, how it's influenced the atmosphere better than the helium line. We traced this down to a contribution from an internal reflection which we had never thought about. And we can now produce routinely and do every day real time from Eve a proxy for this SEM measurement. Well, this didn't happen in the 10 minutes or 7 minutes it took me to tell you about it. It took about 3 years to do this. And it took all these people, the engineers who built and designed SEM and Eve, were sort of really active in working out what this was. Of course, the operators and the flight software people make these things work on orbit. The data systems people, both at USC and here, provided the data sets I needed to do the analysis. One of the things I'm very proud of, both LASP and sort of the few members sitting in this room, is something called the Solar EUV Irradiance Working Group. So it's never just me doing this. This is a whole group of really bright people saying what's going on. And there was enough influence from that group, from the space weather operators who need this product, and also from industry who actually produce some of the models based on this, to say what's going on. We need to solve this. Of course, sort of the scientists here, USC, NIST, the National Institutes of Standards, measured the response function. And as I say, the LASP scientists and the data systems now have a verified product which we put out real time in case SEM goes away. And as I say, we correlate this on a day-by-day basis. Sort of, we are watching this every day to make sure it's tracking properly. So calibration is a really big part of this. And what you're going to notice is that calibration involves concrete bunkers, lots of them. This is the synchrotron ultraviolet radiation facility where I spend way more of my life than I should do. So down here we have electrons whizzing around a ring, and as they this is a circle, as they go around they're emitting photons. And we know exactly what those photons are in energy and polarization and intensity. This is our chamber way back here, so we put our instruments in this. This chamber is this high, same wide, weighs about 5 tons. We can move it in X and Y, theta and phi. It's amazing. And for any vacuum we need 1.4 times 10 to the minus 10 torr is what we achieve. Not in our chamber, unfortunately, that's in the mid 10 to the minus 9s, that's the ring. They don't let us do nasty things there. The amazing thing about SURF is you can see a single electron. Literally, you can look in the port and see an electron. And I had to convince myself that this was real, and I did the math. And yes, it's about 50 femtowatts. And your eye sensitivity is actually about 3 femtowatts in a fully dark adapted sense. So you can not only see it, you can see it quite clearly. And you can definitely see when they step the electrons out you can see changes. It's amazing. So electrons exist and you can see them. So the great thing about surf is that sort of, if you know how many electrons are in the ring, you know absolutely how much power is coming out of them. And that absolute is the scientific absolute. It's not just a hand waving. You know how much power is being radiated from the electron. So this is why this is the calibration facility we go to. And by changing the energy of the electrons, so how fast they're spinning around this ring, you can change the spectrum of them. So you can see in the EUV and XUV, this is why we go there. In the soft X-ray region, you start not getting much power out at all, so surf is not the ideal place to go. We have a really good relationship with the people there, though. Magnets. Several of the instruments we have look straight at the sun, and they're in orbit, and there's all sorts of nasty things, especially electrons, and they come flying down your instrument, and your detector says, I don't know whether you're an electron or a photon. I'm going to count you. So we put magnets in front of them to bend the electrons out of the way. This is actually our GOES instrument. Here you see some huge magnetic coils. They run like this, they run like this, and they run in the other plane as well, which nulls out the Earth's magnetic field. So we can measure how much stray magnetic field our big magnets are causing, which would hurt other instruments. So we are required not to influence other instruments. So we go and measure it. And this is an amazing facility also at Goddard Space Flight Center, where we put the magnet and we shoot electrons into it and we measure how much comes out the other end. This has to be the most amazing vacuum facility I have ever been at, because they still use mercury diffusion pumps. So you boil mercury and it goes supersonic and it pulls atoms out with it. And I thought those were banned so many years ago, but if you go into one of these deep dark basements, you can still find them. Radiation characterization. Of course, we're in space. Radiation is an issue with all of the instruments. It will degrade detectors, it will degrade electronics, it will degrade glass. Again, we want to do the best possible job, so we go and fire protons at these things and measure it. Here we're actually firing it at the magnet because nobody knew whether these magnets would degrade when you threw protons at it. So we threw enough protons at it for something like 20 years mission. We couldn't touch the magnet for 2 days because it was so radioactive. A lot of these radioactivity meters in the places we go to. Here we were testing an ASIC, which Darren is sitting here. Darren helped design this ASIC, and we wanted to make sure that it didn't latch up when it went into space, so we threw particles at it and it didn't. And now not concrete bunters. So this is our solar EUV irradiance working group. We meet about once a year, and when it says working group, it means working group. We sit around a table, we all have hard disks and computers, and we have maybe a day saying, what's the problem we haven't solved yet? And if we don't solve the problem by the end of the meeting, we make sure that we keep on working at it until we do. Of course, we try and choose bite-sized problems, but this is something I'm really proud of. I think this has made a huge amount of progress, both in understanding how these instruments work and making better data products from them. So degradation is the bane of my life. You put stuff up there, you think you've calibrated it well, you look at it and it doesn't give the answer you thought it did. And this is an example which has bugged me for years. Eve started flying. We have two filters, two metal filters, one made of zirconium and one made of aluminum. Now these filters are only 100 nanometers thick. So that's a fifth of the wavelength of visible light thick. It's staggering that you can build these things. You can, they survive launch. but they don't seem to survive degradation. At least the aluminum one doesn't. This is after 4 years on orbit. This MEGS-A filter, it's a zirconium filter, it has not degraded at all to within how much I can measure it. So probably about 1% is the most degradation that filter can have suffered. We look at this aluminum filter, and it's degraded horribly. Sort of this 20% degradation at 17 nanometers. These things are measuring at the same wavelength. They are 8 millimeters apart. How can they be different? The environment they see has to be the same. Sort of we thought, are their temperatures different? No. Are they exposed? Are they charging differently? No. What's going on? So one of the clues was, we went and looked at other instruments. So LIRA is an instrument flown by the Belgians. ESP is another instrument on SDOE that's sitting right next to MEGS. On MEGS-A, ESP, and LIRA, the aluminum filters degrade. LIRA also has a zirconium filter, which degrades badly. Same wavelength, about the same degradation, but the MEGS-A filter doesn't degrade. And this, I was going to write a proposal to NASA to say why, what's going on. And during writing that proposal, before I get to that, we have always modeled this with carbon. We've said spacecraft outgas is junk, the junk sticks to the filter, the EUV hits it, and it polymerizes the carbon and it sticks to the surface, and the filter gets darker. I am as guilty of this as anybody. I wrote a really, really nice paper explaining why this explained everything we saw on even LIRA apart from the one filter. But it's still, why isn't the zirconium filter degrading? So, writing this proposal, I went back to the filter manufacturers and said, what's different to these filters? Why isn't this one working? And they said, well, you made MEGS-A filter with aluminum, there's a little bit of germanium, and nobody actually remembers why there's germanium in it, or why we put carbon on the back. It's like, that's how it was. The ESP filter is just pure aluminum. The LIRA filter is pure aluminum. The LIRA zirconium filter is pure zirconium, whereas the MEGS zirconium filter has carbon on both sides of it. And you think, well, that's bad. You just said that carbon causes degradation, which is what we thought. The carbon actually protects the filter. So what I really strongly believe is happening now is that the surfaces of the metal are oxidizing. I've run models as to what an oxidized surface looks like, and it fits exactly the degradation I see. I have to say that carbon fits it almost as well. I can't find a source of carbon which would do it, though. We have a big source of oxygen. When you launch anything, especially from Florida, from anywhere, the main thing that it is taking up with you, apart from the instruments, is water. It is spewing water out forever, basically. And that got brought home to me really in a big way when Rosetta woke up again, whenever it was, a few months ago. And they couldn't make some of the comet measurements they wanted to because it had taken so much water with it, they couldn't see any water from anywhere else. So we've got water, you show sunlight, and you've got oxygen. Back in 1949, when I looked at the paper, people explaining how UV and oxygen would enhance the oxidation of aluminum. They cared about it for aircraft, but it's exactly the same thing. And we know how to do that. We put what's called a capping layer. So what that carbon was doing on that zirconium filter was not letting the oxygen get to the metal surface. Now carbon isn't, because it causes a loss of transmission, isn't the best thing. I'd probably want to put silicon on there for most of these wavelengths. But the very fact that we can protect these filters is huge. Now again, this has been 4 years' work, which I've just summed up in a few minutes. Took all these people again, the engineers built this thing. Software did it. They not only do this, but they run the calibration routines I need to measure what the degradation is of these filters. I'm not good enough to get this data off the computers or read it, so the data systems do that for me. NIST, the CWIC group, LASP, we have spent ages modeling this. Surface chemistry, to understand how the oxygen attacks the filters. There is a really well understood equation, and I can now modify that equation to work in space, because it has never worked in space before. The filter manufacturers, they really care. They want to build the best thing they can build. EUV lithography, these are the people who make microchips by patterning the masks with these very short wavelengths so they can make much smaller features. They know all about this. They just won't tell you because it's a trade secret, but if you look at them and say, is it oxygen? And finally, I haven't mentioned them before, we have a fantastic administrative group here at LASP as well. So as I said, I'm writing a proposal. I think this is what's happening. I have to prove it, and I have to do that in the lab, and this isn't cheap stuff. Running surf is not cheap. You don't want to know what their electricity bill is, and we have to pay for that. So these people sort of will sit down with you and understand what you want to do and say, that'll cost this much. And I've never been anywhere else where sort of it is so easy to get proposals out of the door. And then when failure is an option and failure happens. Memorial Day last year, it always happens on holidays as well. I don't know why. A fairly innocuous looking email. Something was out of limits. That's a shame. And the page can. She was actually in already. We were doing some other tests. This was a bad one. So first, what's Eve? We've talked about it before. It's a suite of 4 instruments measuring the EUV spectrum. Here's a spectrum which is made of chocolate. We run from about 5 nanometers all the way up to about 105 nanometers. And it's very difficult to do this in one instrument. So the main spectrum, this spectrum is made up of 2 instruments, MEGS-A and MEGS-B. MEGS-A, because I didn't mirror it, measures the short wavelengths up to about 36 nanometers. MEGS-B measures all the rest. SAM, which actually uses the same detector as MEGS-A, is a pinhole camera which makes these lovely X-ray images of the sun. Low resolution, but it's all we need. It tells you where the flares and active regions are. And ESP, this other, it's a broadband instrument which we built at USC. When we first launched, we suffered damage to the CCDs. This was, it's a real balance when you're building these instruments is how much radiation do you want them to tolerate? You know the detectors are going to get worse with radiation, so you actually pre-treat them so that you don't see the first part of the degradation curve. It's just, you're just blind to it. And then when the radiation gets worse, the detectors get worse and worse and worse. So we designed these CCDs to show no radiation damage until about 5 years on orbit. Unfortunately, the moment they tried to insert SDO into its geosynchronous orbit, so you launch into a fairly low orbit and then you raise the orbit into a geosynchronous orbit. The moment they did that burn, it cut itself off automatically because there was too much sloshing in the fuel tanks. And that took about 2 weeks to solve, and unfortunately we were now going through the radiation belt twice a day. So we got more than our total mission life of proton damage before we even got to orbit. Unfortunately, this is a much more of a problem for that longer wavelength MEGS-B channel because the photons just don't go very deep into the silicon. So we try to limit the exposure of sunlight to MEGS-B because the more sunlight it sees, the worse it gets fairly fast. And this didn't really matter much when we had MEGS-A because we got the important part of the spectrum. And then this capacitor failed. I won't say a 10-cent capacitor, it's a space capacitor, so it's probably a $10 capacitor. One capacitor failed. And I've always wondered, sort of, when you hear about these review boards and they say, Ooh, it was that thing which failed. How do you do that? Within 2 days, the electrical engineer said, it's C137 which has gone. And it's shorted. And it's like, wow. And then we said, there may be a chance you can recover it. If you cycle the power quickly, you may actually put enough heat into that capacitor to blow it up. Okay, what's the worst that can happen? It doesn't work. It didn't work. Unfortunately, it's a failure. We now understand that this particular geometry of capacitor and the fact that we had built this instrument so well that we couldn't overcurrent this device. We couldn't do it. MEGS-B is still working okay. It's the degraded detector. So what we've done so far is we've scheduled when we make measurements, but that means we don't catch many flares. We really want to measure flares, so how do we do that? We have ESP working. It is measuring flares real time. Every quarter of a second, we get data. But you can't have that data coming down to the ground, somebody looking at it saying, oh, there's a flare, calling the operator at Goddard and saying, can we move the filter wheel on MEGS-B to make an exposure? We don't staff 24/7. Goddard doesn't staff 24/7, and none of us want to be doing that. So how do we do that on board? We have data for 4 years. So I have looked at every single flare seen by ESP and MEGS-A. And I wrote an algorithm which just says, if the level is above this and below this, and it's rising at this speed and not faster and not slower, move the shutter wheel. We do not false trigger at all. We capture most flares greater than M1. It's great, but this is, as people are fond of saying, this is scientist code. So we have to do something about that. But anyway, let's go back. So this is the whole MEGS-A story. Again, who do we need? To understand this CCD degradation, there was a whole gang of us. Double E's, scientists, people at Goddard, people in Europe who have seen similar degradation of their CCDs. We understand exactly what is happening to these CCDs. Unfortunately, it is exactly what happened to CCDs on SOHO, which degraded this way. We don't know how to solve this problem. CCDs degrade with proton radiation. It's a balance. We try to anneal the detectors, we try to warm them up and get rid of these defects in the silicon. We didn't see any improvement in the detectors, but we saw a huge hit on our ability to calibrate this instrument. So we gave that idea up. So we modified the way that MEGS-B makes these observations, so it takes 3 hours of data a day. That's enough information that the modelers who are saying, what is the solar output doing to the Earth's atmosphere? They get enough measurements from that, but we don't get flares. MEGS-A failure, again, it was the operators who called us and said, something's gone wrong. And they immediately made sure that the instrument's safe and nothing else would go wrong. We then probably spent about 2 weeks, but within 2 days, we knew this capacitor had failed. MIT actually built this CCD camera. We had fantastic expertise here, and the parts engineers at Goddard Space Flight Center who are the ones who said you can blow up the capacitor if you're lucky. Again, we can't do any of this without data, and it was engineering. The operators ran special routines to collect data faster than we ever normally collect data when we switched on to see what was happening. Again, this all was trying to fix the problem. We couldn't. In the end, we said, this is it. We don't want to risk doing damage to any of the other instruments, so we switched it off and make sure that in any of our operating modes, MEGS-A doesn't switch on. So to try and do this flare figure, again, it was Data Systems created for me a data set which looks exactly like the data actually sitting on the spacecraft. So I could run this science code to see what would happen. We produced a proof of concept that we can trigger this. And now flight software has to do the real job. They have to say, okay, we'll take your really messy code and we will make it so it will work autonomously without failing on a spacecraft. This is going to come within the next couple of months, which will mean that all our operating procedures change again, all our data products change again, but I get flare spectra to play with. So again, out of failure, we get success. So I mentioned CubeSats, and I'm going to talk about them very briefly. We have a CubeSat called MEGS, which is going to launch, James, in a few months? June. This has been mostly a graduate student project. That's MEGS. That is the whole thing. That is the solar panels, the attitude control system, the communication system, the science instruments. It all fits into this, and it points at the sun, and we will get continuous soft X-ray solar spectrum when this thing launches, for the first time ever. And students built this, and it's this big, and it's fantastic. And I get to help too. I can't go and touch any of these flight things anymore. This is it. We are building two of them, Flight 1 and Flight 2. Flight 1 has just come out of thermal back testing with a couple of very minor issues. It is going to be delivered in April and launched in June. We're still looking for a ride, so if anybody had a spare rocket, we have another one ready to go. This is a big thing for the future. This is where failure is an option, has to happen. We have to be able to test new instrument concepts and really far out things. So far, most of these CubeSats have been built as student projects, both here. The Air Force have built a few, which I'm sure some people know what they do, but I don't. We want to get into sort of building real scientific measurements on CubeSats. This means it doesn't cost $1 million. It means we're probably looking at sort of $5 million. But that's not $500 million or $1 billion. So you can still test stuff on this. So we're working on a concept called CSIM. So some of you know what the solar irradiance monitor is. It's a very broadband, very high accuracy UV visible near IR spectrometer. We think we can fix this into something which is 6 U's. So that's 20 centimeters by 10 centimeters by 30 centimeters. It's tight. We think we can do it. We want to look at flying constellations of CubeSats. So this is lots of them. So if one fails, it doesn't matter because there's another group up there, and you can constantly be renewing your technology. So you sort of have a mothership which is doing all the communications, and sort of this one is measuring the sun, and this one's doing this, and this one's measuring plasmas. And I think that any satellite you fly now should be able to talk to CubeSats. It's a fantastic thing. But because they're small doesn't mean they're cheap. I think this is a mindset we have to get rid of. And sometimes it's more expensive to shrink this stuff. The optics certainly gets much harder. GOES is going to fly. We have the instruments ready to fly. They are sitting on the spacecraft but not integrated yet. It will fly one day, which will give us another new generation X-ray instrument, not imaging unfortunately, and new EUV instruments. We're continuously trying to make better instruments. I would love to build an imaging X-ray spectrometer. And we continue to work on making better instruments. So this was originally the title of my talk. Why LASP? So I've worked at all these places, and why here? Well, first, I feel like I fit in here, and being a true nerd, I actually calculated where I fit. These being the distances from each discipline that I work in. You get to do this. This is a calibration sounding rocket for the SDO Eve instrument. So we built an exact clone of Eve. We take it to the concrete bunker itself and calibrate it before we put it on the rocket. We fly it. It is now looking again at the same sun that our on-orbit instrument is looking at. And you can see here, it is just about to lock on the sun. Get about 5 minutes worth of data. We then take it back to Earth after it's landed, calibrate it again to see if there's any degradation during the flight. So here, this is, you can see various bits that, I don't know quite what that just flowed.
What's your altitude here?
So the altitude is measured here, it's 155 kilometers. So we're just starting to get enough above the atmosphere at this point that we're taking real data. So now we're pointing at the sun. We're fixed, staring at the sun. And these rockets are now amazing. They are pointing us within an arc second of where we're asking them. Rock solid. So you can see here we're coming up to apogee. All the time taking data, we get a subset of that data coming down to us real time so we can just feel comfortable that it's all working. So we're now 5 minutes into the mission. When you're actually running this thing, it feels like about 2 seconds has gone past. And you're wondering, did it work? Are we going? Coming down now, you'll see that we lose lock on the sun. You can see the Earth is gradually coming, so we're starting to get a little bit of atmospheric influence on, and then we just lose acquisition totally. And here we go. And you'll hear, now it's starting to be in the atmosphere, they're firing gas jets. So this spinning is deliberate, because you're re-entering the atmosphere and you want to spread the heat all over the rocket skin. So I would not want to be on this flight. And so now that is the most happy sight of any rocket launch. So the drogue chute has gone out, so you're slowing down and here comes the main chute. So you are not going to splat. So at this point, they haven't blown you up and the parachute is out. So you can breathe again at this point. So far, all the landings, we oversized the parachute on this because we want to refly this. This is, I think we've flown this particular Eve experiment 8 or 9 times now. We want to fly it at least 3 more times. So by having a really big parachute, you get a nice soft landing, although it's not going to look quite that soft. We have not done any damage to this payload at all. The payloads I used to fly at USC would come back bent because we hit so hard. Here you see the shadow of the rocket. You see how it looked like that first spectrometer I built? And after this, the helicopters come, pick it up, bring it back, we take it all apart and drive it back on the truck. So this is fantastic. This makes my life really fun. But the real reason is these folks. There is always somebody here who knows more than I do. And they are always happy to let me know. And I learn something new every day. So that's why LASP. That's why instrument scientist is so much fun. Thank you. Any questions? Dan.
What would it take to build the solar X-ray imager?
So my idea is very simple. We saw on SAM, this was an add-on to Eve. Tom Woods was the principal investigator on Eve, and he said, ooh, we've got a bit of spare area on the CCD, let's put a pinhole camera there, then we can look at the sun, say how well pointing we are, and this sort of thing. And then it was, ooh, we'll put a beryllium filter in, and we'll measure the X-rays. And we had hoped on Eve to measure spectrum. The filter wasn't thick enough. So the trick is to measure single photons, so you can tell how much energy they have. On Eve, we were limited because we had to have 10-second integrations for the EUV part of the CCD. So I think you can build a CMOS camera now, which just goes incredibly fast. So maybe sort of 100 frames per second. so that you would never get more than one photon hitting the pixel at the same time. Now, you obviously don't want to send down sort of the full image, but if you just record which pixel it hit and how much energy you deposited, you would build up the spectrum and the image really fast. So I'm thinking fast CMOS camera with a pinhole and a beryllium filter.
So
Not
it's
difficult.
Just waiting to be built.
Just waiting to be built. We have the detectors. So yeah.
Where do your CubeSats have to fly?
So James can probably answer that better.
Where do they fly?
Where? So these are all low Earth orbit. Is it that what? That's the question, or where do they fly from?
I meant how low.
How low? Is it 500 kilometers or so?
Sicily's going up to 780.
So they're all low Earth orbit at the moment. We just
I work in orbital degrees.
Oh.
This one.
Oh, so that's actually one of the things which drives us, is that we have to prove that we're deorbited in 25 years. So that's why they're low. Having said that, we just the day before yesterday, learned that a proposal we'd put to fly a CubeSat to the L5 gravity null. So the Sun-Earth gravity at sort of 60 degrees, we wanted to put a CubeSat there. And we had worked out the orbital mechanics to get it there. So again, that wouldn't cause debris because it would just keep on going. So CubeSats are going to be the thing. Sort of. We really want to put a constellation of CubeSats at L5 and at L4 for space weather, because you can look at stuff coming around the disk before it gets to you. And we cannot model solar activity well enough to give the warning which aircraft companies, power grid operators, everybody wants to know what the solar weather is going to be days in advance. We don't understand the sun well enough to give a forecast, so if you can look and see what's coming around, you have a leg up. So that's going to be in the future sometime. Yes, James.
You said that all these rocket launches and everything, they bring a lot of water with them. So
Yes.
And I know that planetary exploration, they really care about not contaminating things. So do they do special stuff to prevent that?
I don't think there's any way that you can't. Water seeps into matter. So the major contribution when we put anything in a vacuum tank, as long as you haven't spooged it with oil or something, touched it with your fingers, is water. It buries into aluminum and gradually comes back out. And there is, you can do things to speed it up, but it is going to come out for years and years and years. So Rosetta has been up there for 10 plus years. I don't remember when they launched that. Okay, it was cold, so most of the water was frozen. The moment they heated it up, this cloud of water came.
Andrew, for Europa, they're planning to heat things up, I think, to 110 degrees C to decontaminate. Would that get rid of the water?
It'll get some of it, but you'd have to heat it for almost infinite amount of time to get rid of all of it. It's something that sort of, I think I can solve this problem just by putting carbon or ruthenium or silicon on top of the filters to stop them oxidizing. And what was just, it was eye-opening is that sort of people have known about this since the 40s. And just because we don't read surface chemistry of aircraft frames, we all know that aluminum oxidizes in air, but it's always been said, oh, it forms a self-terminating layer at about 4 to 7 nanometers. Yes, it does in the air on the ground. You show it UV light, it keeps on eating its way down to about 30 nanometers. So, you know this stuff, or some people know this, and they know the solutions, and so that's what's just so much fun about this. Yes?
Were you able to test any of those out on the rocket launches, the suborbital ones?
You could, but the huge advantage of doing this at SURF is that we can put about 13 years worth of EUV exposure onto a filter in about 10 minutes. So yes, we could fly flights. You can't handle, we land in a desert, you can't handle these filters in any really pristine way on a rocket flight. So our plan is that we will have a pristine filter prepared actually in a vacuum system, so we know that it's not oxidized to begin with. Shine light at that, EUV light at that one, and a standard filter, and a filter which has an oxygen atmosphere, so we can control it much better. It's also much cheaper. So surf isn't cheap. Rocket flights are about $2 million a shot at the moment. So it's a possibility, but I would really much prefer to do it in a controlled lab. And that's part of the problem, is that NASA said, oh, you're doing lab work, NSF should pay for that. And NASA says, but you're doing it for a space program, so NASA should pay for it. So NASA's actually, in the last year's proposal, had a lab-based nuclear physics program. So everybody keep your fingers crossed that we get some money to solve this problem after all these years. Jenna?
What variables would you like to try for testing different counting layers?
So I think, so the main thing is what their transmission band is in the EUV. So carbon works really well on zirconium because zirconium only transmits up to about 26 nanometers, and carbon is still fairly transmissive there. If you wanted to cap a filter for MEGS-B, for instance, you would have lost sort of 3/4 of your signal before you got to 60 nanometers. One of the things which the folks at NIST have played with is a hydrogenated silicon, which is really fairly transmissive sort of all the way in the bands we're interested in. So that would be my number one choice, is to see if what works for the EUV lithography people would work for us. The filter manufacturers say, yeah, we're pretty sure we can do that. It also opens up the choice of other filter materials themselves. So we've always wanted to fly indium filters or tin filters because they limit the wavelength band you're looking at in different regions. The problem is you look at them and they're oxidized. So we're wondering whether we can actually make these filters now with this hydrogenated silicon on both surfaces and still get sensible pass lines and sort of open up sort of these filters which would make instrument design easier. So that again, I would really like to try and make those. Anybody else? Okay, I'll just, as you go, you can watch one last movie. You saw how fast the sounding rocket launched? This is SDR. It takes 10 seconds to clear the tower. We're almost in orbit in 10 seconds on a sounding rocket. It is fantastic. If you ever get a chance and you haven't seen one of these launches, try and find a chance to go and see one. It is just amazing.
And that was probably fast compared to Maven, if I remember.
Yeah. This is it going through Mach 1, and you can see the shock waves.
What launch vehicle was that?
That's an Atlas 5. Okay, thank you again.